Okay, so today's goal will be to determine the matrix associated with a linear transformation. So if we start from a linear transformation T between two finite dimensional vector spaces V and W, and moreover, we are given a basis B of V and a basis C of W, then we can define the matrix TCB associated with this linear transformation. So if V has dimension n, W has dimension m, then this will be a m by n matrix. And the interest of such a matrix is that whenever you have a vector v in the vector space, a big V, which is expressed in the basis B, and you multiply that vector by the matrix TCB, then you get the image of the vector under the linear transformation in the basis C. And so there is one formula for this matrix, which goes as follows. So if we list the vectors of B from B1 to Bn, then the matrix TCB, it has columns, so this is definition, it has columns given by the image of each of these basis vectors expressed in the basis C. So TB1 in the basis C, TB2 in the basis C, all the way to TBn in the basis C. So this is what we are going to do today, and we will do this through 3 examples. So let's go on to the first example. So first example will be of a rotation. So we will take as linear transformation a linear endomorphism of the plane, which is rotation by an angle of theta. So if we start with the vector v in R2, we will look for the matrix that represents the linear transformation rotation by an angle theta. And for that, we only need to find first what is the basis here of R2. We will take the canonical basis. So two vectors 1, 0 and 0, 1. And here C is just the same as B. And now what we need to do is to find what is T, the rotation of an angle theta of the first basis vector, which is rotation of the vector 1, 0. And so if we look, 1, 0 is on the unit circle. And so if we draw a picture of what is going on, we look at the unit circle here. It goes through the point 1, 0. This is the first basis vector. And then when we rotate it by an angle theta, we get the vector here cos theta sin theta, right? So t of 1, 0, it will be cos theta sin theta, sine theta. Now, remains to do the same, find the image under this linear transformation of the second basis vector, B2, which is the image of the vector 0, 1. And now, if we start from the vector 0, 1 here, 0, 1, and then we perform rotation by angle theta, what do we get? We get the vector minus sin theta cos theta. Now, if you remember the formula from before, then the rotation, the matrix associated to this rotation with respect to the bases B and B, it is given by T of B1 in the basis B and T of B2 in the basis B. And here, this is simply cos theta sine theta minus sine theta cos theta. And here we found the matrix associated to this linear transformation. Okay, so if, for example, we take, if you want a more concrete example, and we take theta rotation by pi over 2, and we take as vector v in the canonical basis vector 1, 1. So this is this vector here, 1, 1. And then we apply to it a rotation by pi over 2. What should we get? We should get the vector minus 1, 1. But in this case, the matrix of the linear transformation, it's cos theta, which is 0, 1, minus 1, 0. And then when we multiply the vector 1, 1 by this matrix, we obtain indeed minus 1, 1. So now we can go to our second example. Which is a sample function. So our second example, it's a linear transformation from the vector space of polynomials of degree at most 2 with real coefficients. And it goes to R3. So here, this is the space of polynomials of the form ax squared plus bx plus c with a, b, c real numbers. Right? And we will look at the linear transformation, which is given by sampling at the polynomials at 3 different points. So we take 3 real numbers, x0, x1, and x2, which are all pairwise distinct. So we take x1 is not equal to x0 and not the same as x2. And so they are all distinct. And now the linear transformation is given by, you take a polynomial p, and then you evaluate it at these 3 points that you have chosen in R. So you evaluate p of x0, p of x1, and p of x2. Now, the canonical basis for the space of polynomials, it's made of these 3 polynomials: the constant polynomial 1, the polynomial x, and the polynomial x squared. You can express any polynomial in P2 as a linear combination of these 3 polynomials. And then, as before, we will take C, the canonical basis of R3, which is given by the three vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And now, so our task now is just to determine the image under the transformation of these three basis vectors. So we want to determine what is t of the constant polynomial 1. Well, it is the constant polynomial 1 evaluated at the point x0, the constant polynomial 1 evaluated at the point x1, and at the point x2. And since by definition this is the constant polynomial with value 1, at any point it evaluates to 1. So we get the vector 1, 1, 1. Now if we do this for the polynomial x, well, when you evaluate it at x0, it gives you x0. When you evaluate it at x1, you get x1. When you evaluate it at x2, you get x2. Finally, if we take the image of the third basis vector, you evaluate the polynomial x squared at x0, x1, and x2. And now, if you combine all of these together, you get the matrix we are looking for, which is the matrix of the linear transformation T with respect to the basis B and the basis C, and which is given by these three vectors as columns. So 1, 1, 1, x0, x1, x squared, it's x2, sorry, and x0 squared, x1 squared, x2 squared.